Doing this special case where n equals 2 and p equals a half. So it's a very low number case. Like in general, we want to know the binomials for any n and p. This is some simple example where the mean is 1. We saw that the mean is the n times the p, 2 times a half. That's why it's 1. Now we want to do the expected value of x squared. What is the expected value of x squared? What did people say? All right, lots of people have no idea. That's great. We're going to learn. Some people said 1. That's also a tempting thing. You might think the expected value of x squared is the expected value of x squared, and then you get 1 squared. What am I trying to say out loud here? You might be tempted to believe the following. Okay, this is a different class. So you might be tempted. You remember we learned some tricks. Like, for example, we learned already that the expected value of x plus y equals the expected value of x plus the expected value of y. Well, that was something we learned. And it even works with numbers. So you do like expected value of x plus 3 times y. That's the expected value of x plus 3 times the expected value of y. This is all great. So that's very good. So you might be tempted to think, oh, the expected value of x squared, that's the expected value of x squared, right? So if you can do stuff inside, then you should be able to do this. Unfortunately, this one is wrong. So don't do this. This is all wrong. And expected values are linear. E obeys linear stuff. Obeys linear. So as long as the thing you're doing is linear, you can do it. This is nonlinear. So don't do that. Don't do this. Nonlinear. So if you said 1, maybe you did it that way. It's a good life lesson. This is wrong. Okay, so that's one thing. So 1, 1, 1, lots of people didn't know. That's great. Now I will tell you. Some people said 1. The next most common answer was 1.5. And 1.5 is correct. So if you got 1.5, that's very good. Let's see how you get 1.5. And I'm going to show you 2 different methods to get 1.5. So here is method 1. This is like the straightforward calculation. The calculate, no tricks. Calculate, no tricks. Okay, and really what you do here is write down the probabilities. We saw a minute ago that x for a binomial 2, 1/2, you can write down this kind of thing. You can write down all its probabilities. It's either 0, 1, or 2, and the probabilities are 1/4, 1/2, and 1/4. That is what we said. And here's my little funny notation for writing down the possible values. You could also write it another way. You could say the probability x equals 0 equals ... Sometimes people just say p of 0, p of 1. However you want to write it down, you have the values and their probabilities. And if you have the values and the probabilities, you can compute the expected value. So let's do that, just to make sure everything is sane. You can compute the expected value. The expected value is the average of all these things. So 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4, right? Taking all the values here, 0, 1, and 2, and multiplying them by their respective probabilities. 1/4, 1/2, and 1/4. That's the expected value, and that should work out to 1. 1/2 plus 2 times 1/4 is another 1/2. That is 1. So that's one way to do it. The very honest, straightforward, using what we know about expected values. Let's do the expected value squared. That was what the question was asking for. And when you square it, you literally square all the values. So it's either 0, 1, or 4, and it has those same probabilities. 1/4, 1/2, or 1/4. And so the expected value of the thing squared, same kind of situation, except instead of being 0, 1, 2, now it's 0, 1, 4. 0 times 1/4 plus 1 times 1/2 plus 4 times 1/4. Okay? Same kind of thing. And if you add this up, you should get 1/2 plus 1, 1.5, 1.5. Also known as 5/4. So this is a formula. This kind of thing that we just did over here, so you use the probabilities, the same probabilities as before, but now you take all the values and you square them. So you know this was 0, this was 1. Let's write this 4 actually as 2 squared. 2 squared. So that's a formula. This formula has a really funny name, which is called the law of the unconscious statistician. I don't know why it's called this. Law of the unconscious. But if you want to look up the Wikipedia page, the unconscious statistician, and it just says, do the thing. If you want to know the value of x squared, you square up the yellow values, and then you multiply them by the green probabilities. That will give you the expected value of any function of the original random variable. That's the law of the unconscious statistician, and that's the first way to do this problem. If you got 1.5, did you do it this way? Who did the problem this way? A few people. Okay. Any questions or comments about this calculation? Of course, I'm assuming you remember the formula from the video. Maybe I'll write down the formula one more time. Expected value of x is the sum. This means sum of x times the probability that capital X equals x, sum over all possible values. That's the formula that I'm using. And the law of the unconscious statistician says if you want to do any function, you apply the function to x. You do the sum of g of x times the probability x equals x. That's the unconscious statistician, summing over all the values. And don't be scared of these sigmas. They just mean add up stuff. So if you understand it with this concrete example, that's all we're looking for. This is a fancy way of saying this.
Mihai?
Yes?
Slightly conscious statistician, the 1.5 equals 9/4.
Oh, yes, that's very good. A very good catch. Maybe equals 3/2. 3/2. Okay, let's go with that. That's very good. Okay. So this is one way to do it. Now I'm going to show you a different way to do it. And the reason we need a different way to do it is because this method works great for 2.5. So n equals 2, p equals 1/2. Fantastic. Gives you the formula. But you can imagine if n equals 7 and p equals 1/3, you got a lot of stuff to add, and it's going to get quite complicated. The probabilities, these individual green probabilities, are quite annoying and complicated. So I'm going to show you another method that scales nicely and is easier to compute. And that is exactly using the tricks we learned before about adding stuff together. So this is a use x is a sum of indicators. That's what we did last class, a sum of independent indicators. And so this is a really nice trick to let you get the same answer. And you'll see that once you know this trick, you can answer all sorts of harder questions. So what I'm going to do is instead of doing x squared on its own, I'm going to write x equals I1 plus I2, where I1, I2 are independent, and they're Bernoullis that are either 0 or 1 with probability 1/2. So the probability is 1/2 for each of these. Okay, why is this useful? Well, you saw in the video, if you take the expected value and you use linearity, you can quickly get the expected value by just adding up the p plus p. So it's very good for taking the expected value. And now I'm going to show you the expected value squared. So here I'm going to write x squared. X squared is I1 plus I2 squared. And I'm going to square it and then take the expected value. And to do the expected value squared, you could do it all algebra. So you could do I1 squared plus I2 squared, square the first term, square the last, double the product, math's a blast, right? Okay, so there we go. I1, I2. And then you could do the expected value. This is the algebra way. But I'm going to do a picture version of this, because that's even more exciting. So let's do a picture version of this. And here I'm going to have a little square, a 2x2 little window. And I'm going to write in I1 squared, I1, I2, I2 squared, and I2, I1. And this is really a visual interpretation of where this rule for squaring comes from. If you multiply I1 plus I2 by I1 plus I2, then you're really doing this addition of things. So this is like why the square the first term, square the last, double the product, math's the blast rule works, is because you have a sum of two things times the sum of two things, you multiply them in all the ways, you add it up. And the nice thing is now, when you do the expected value, we're going to do the expected value of all the terms individually. So x squared is this. The expected value of x squared, the average value, we know averages play nicely with adding. So you can add up all the individual expected values, and that's saying, in the picture, you can add up the expected values of these individual things. So you can do the expected value of all these pieces individually. Okay. What are the expected values of these pieces? Let's do some analysis. First of all, what is I1 squared? I1 squared, that's taking the value and squaring it. I claim that I1 squared actually is just equal to I1. why is it actually equal to I1? Well, look, I1 is either 0 or 1. If you square 0, it's still 0. If you square 1, it's still 1. I1 squared is the same thing as I1. It is either 0 or 1 with the same probabilities. So that one is no problem. So what's the expected value? That's going to be a half. Half the time it's 0, half the time it's 1. So on average, it's a half. Same thing with this one. This one, I2 squared, is just same as I2. On average, that's a half. This is very tricky when you first see it. You're like, how could it be that a number squared equals the number? That seems insane. But it's just that it's always either 0 or 1. And 0 squared is 0, and 1 squared is 1. So it doesn't change when you square it. Very tricky. Yeah?
Does the 0, 1 stand for like success and failure?
Yeah, that's right. Okay. That's right. So remember, we're counting up the number of successes. I is it's called I for indicator. It's indicating that there was a success in the first little bit. So we have I1 and I2. Did you get a success in the first one? Did you get a success in the second one? Add them together. That's the total number of successes. Yeah, great question. Okay, so that one's nice. What about these ones? I2, I1, and I1, I2. Now is where we use what we learned last time, is that when things are independent, you can split up the expected values. So because I1 and I2 are independent, by the independence rule, the expected value of I1 times I2 is splitting up as a product the expected value of I1 times the expected value of I2. It's the product of these two things. Another way you could do it is you could think of probabilities. So I1 is either 1 or 0. I2 is either 1 or 0. What is I1 times I2? For that one to be non-zero, they both have to be 1. So this is really asking what's the chance that I1 equals 1 and the chance that I2 equals 1. And because they're independent, it splits as a product of the individual things. So in this situation, it's quite simple. In general, we're using the formula for the expected value we learned last time. So this is independence implies uncorrelated that we learned last time. So this is the independence rule. From last class. Okay. And in this case, they're both a half. So it's a half times a half, which is a quarter. So very simple. A half times a half is a quarter. So here we go. This one is a quarter. This one down here is a quarter. And now you add them up, right? So we have this nice little square. A half plus a quarter plus a quarter. That gives you the answer, which was 3 halves. That's one. That's another half. 3 halves altogether. So we did the question 2 ways. One way was maybe a little more straightforward. The other way is a little more tricky, using this splitting up as the independence. But now I'm going to do something more complicated where the first way just does not work at all, and the second way still works. It's still nice. It's also like the end of the video. We did the same thing with the expected values. Now we're doing it with the expected value squared. Yeah?
Will this note be posted online after the lecture?
Yes. Yes, I can post the note online. Yeah. Any other questions? Okay, let's do it. Now I want to do it in general. So I'm going to do it for what is the expected value of x squared when x is binomial of np. And so the answer is not going to be some number. It's going to be something that depends on n and p. Okay, and we're going to figure out what it is. And the problem is if you try to do method 1 is impossible. Method 1, you have to do this sum. You have to do the sum of x squared times n choose x times p to the x times 1 minus p to the n minus x. And you have to add this up from x equals 1 or 0 to n. This is impossibly difficult. Impossibly difficult.
Difficult, not impossible.
Okay, all right. For me, it's impossibly difficult. If you're a superstar, you can do it. Okay, let's say difficult. Too hard, very hard. How do you do this sum, Gary? What's your?
It's got a couple tricks in it.
You got to do. The only way I know how to do it is you got to use a generating function. If you don't use a generating.
You don't need a generating function.
Okay.
I've got it, but I couldn't do it off.
The only way I know how to do it involves something called a generating function, which is like hardcore combinatorics. You really gotta. But okay, we're not gonna. But fortunately for us, we're not gonna do this. So don't worry, guys. We're gonna do it the easy way. The easy way. Okay, and easy is maybe an understatement. It's still gonna be tricky, but at least straightforward. And I'm just gonna write, like I did before, x is the sum I1 plus I2 plus ... plus In, where each I k is Bernoulli. The Bernoullis, they're this thing, they're 1 with probability p, and they're 0 with probability 1 minus p. So same split up as before, and the thing we know is that each of them individually is like this, and we know all together they're independent. All independent. Independent. Okay, so that's what we're going to do. Let's do the same thing we did before. When you want to do x squared, you just write a big rectangle now. So x squared, you got I1, I2, ... all the way up to In. I1, I2, all the way up to In. That's on the top. And then on the bottom, you also have I1, I2, all the way up to In. So this one becomes I1 squared. This one becomes I2, I1, In, I1, I2, I1, I2 squared. All the way over here, we're going to have In squared. In, I2. All the way down here, we're going to have I2, In. And here we're going to have In, I1. Okay, so there's a lot of ... dots in my grid. ... It is the big version of the 2x2 grid I had before, where now I have, it's an n by n grid. So there's n rows, and n columns. So it's an n by n square, and it's filled in with the terms I1 plus I2 plus In on the top and the bottom, and when you square them all, you get this. This is the n by n version of square the first term, square the last, double the product, math sub last. It's you square the first term, you square the second term, you square the third term, you square the fourth term, ... square the nth term, then add up all the different ways that you can do products of them. So the rows here are the first term, and the columns are the second term. Okay. It occurs to me, if you've never seen anything like this before, this might seem a little crazy. If you've seen stuff like this before, you're like, oh yeah, this is a cool way to organize my algebra. I don't know which camp you're in. Ask me some questions. Yeah?
Sorry, this isn't random, but I know In and Ik, those are the same thing, right?
Yes, so In is the nth one, and Ik here means, like, think of one of them, right? So like the kth one, k could be any of them. K equals any of the numbers. So that's a good question. So n is like the last one, and k is like an anonymous variable. That means could be 3, could be 4, and I'm just trying to say all of them are like this, and they're all independent. If I just said In is Bernoulli, you say, well, what about I3? Well, so I'm using k as an anonymous variable to stand for all of them. Yeah?
I don't think the class is like a tangent direction, but if you were going to rewrite that like in a matrix.
Yes, it's a matrix. That's right.
Yeah, but like what would an structure?
Yeah. So that if you want to write it as a matrix, you can say this is a matrix where Mij equals II times Ij. So it's a matrix where the thing in row I, column j, is II times Ij. I probably should avoid the letter I, but this is what it is. So if you like matrices, that's what it is. If you don't like matrices, that's what it is. You don't need to know this notation to understand this. That's what it means. Okay, so it looks very complicated, but now I claim that actually, even though this looks quite complicated, when you take the expected value, it's going to be quite simple. So even though this looks complicated, we're going to do the same trick we did before of taking the expected value of all the entries. This was the 2x2 case. And the entries on the diagonal are going to be one thing. The entries off the diagonal are going to be another thing. So I claim that when we do the expected value, we're going to get the same kind of picture, and it's going to look like this. So do the expected value of each term. Okay, what are you going to get? On the diagonals, I claim it's going to be p. When you do the diagonals, it's going to be p, and then there's going to be another p, dot, dot, dot. There's going to be all the way p. So all the diagonals, I claim, have expected value p. And that's because the expected value of any number squared, so ik squared, k could be any of them, that is the same as the expected value of ik, right? Same idea as we did before. Before k was 1 or 2, right? We had I1 squared or I2 squared. Same idea. It's going to be p. So you don't change anything. This is equal to p. So the diagonals are all p. Questions about that? All right. What about on the off diagonals? What about on the off diagonals? You know what? I've been doing a lot of math here, and I haven't maybe given you a chance to think. So why don't I phrase it as a question for you? What is on the off diagonals? What is on the off diagonals? So in my little matrix, after taking diagonals, ooh, I'm spelling words wrong on purpose, and you'll see why later. Okay, but so for now, ask yourself, what goes here? When you take the expected value of, I don't know, I and I2, what should that be? What's going to go there? I'll give you a minute to think. This maybe will let you digest a little bit. What goes on the off diagonals? I'll give you 1 minute. You tell me, and then we'll put it in a box right here. Okay. Feel free to chat with your neighbors and discuss.
So right now the puzzles are so you can start it all. That's fine. And then once you start That's the right final answer. That's the right final answer. But why is that formula true? Yeah, you got it.
Okay, time is up. I'm glad I let people think for a bit because I heard some people yell out the right answer right away. So this is great. This is giving me some confidence that you guys are with me and I'm not just talking to myself over here. Somebody said it is p squared. P squared. And that's the right answer. Why is it p squared? Well, it's the expected value of two of these things. So it's I something. Let's do an example. Let's do I2IN. That was one of them on this list. So let's do this one, for example, right here. I2IN. That's this one. Well, they are independent. I2 and IN are independent. So you do the product of two different ones. I2 times IN. P times P, also known as P squared. So by the independence rule, it splits as a product of two things. Each of them is P. It's P squared. So you got this big old box of numbers. A lot of the numbers are P squared. There's a bunch of P squareds. And the ones on the diagonal are P's. And you got to add it all up. So n by n box, the diagonal says P. The off diagonal, anything not on the diagonal, says P squared. That's what we do when you get the expected value. And now we can add it up. So the answer is going to be the expected value of x squared is the total, and that's something times p, so the diagonal, number of diagonal terms, number of diagonal, how many were on the diagonal, plus, then we're going to have a bunch of p squareds, where the p squareds is number on the off diagonal. Number, let's say not on diagonal. Not on the diagonal. So that's what we got going on. How many things are on the diagonal? Well, it's an n by n rectangle. Well, square, really. That's n times p. How many are not on the diagonal, where there are n squared numbers in total, and n of them are on the diagonal? It's n squared minus n. And that's times p squared. So that's the final answer. We've computed a very hard calculation by doing it in a smart way and organizing it in a little box. And you had to be a little clever to do this and count these up. But all of the steps individually are not so bad. You don't need any crazy hard math or anything. You just need to know about adding things and counting basic things. Any questions or comments about this x squared? There's a great question to ask, which is, why are you torturing me with this? Who cares what the expected value of x squared is? Why would anybody care about such a thing? Well, it turns out there is an important concept in probability that is called the variance. So here's a new definition for you, which is the variance. The variance of a random variable. The variance of x. And the variance of x is defined to be the expected value of x squared minus the expected value of x all squared. Do you remember at the beginning I said this thing is not equal to this? That's a bit like saying the variance of a random variable is not 0. So this thing is not equal to this. If the squared is inside the bracket or outside the bracket, you get two different answers. Maybe I should add even one more bracket to be safe, a little safety bracket. And we have just calculated the variance of a binomial random variable. So example, the variance of the binomial random variable, let's say if x is binomial np, then the variance of x is what? Well, it's the formula we just did. Well, let me copy the formula. np minus n squared minus n times p squared. And then you got to subtract the average of x. Well, the average we did a couple classes ago. It's n times p all squared. So that's the variance of a binomial random variable. And you might notice there's some cancellations here. You got an np, you got an n squared p squared. Hey, there's an n squared p squared over here. So the n squared p squared here cancels with the n squared p squared over here. If I was being okay, let me write it out. I know people don't like it when I do things in brackets. So let me write one out. One more step out. Minus n squared p squared. And now, oh no, this one's a plus. Okay, good. My world was almost shattered. Okay, there we go. Now these things cancel. Okay, so this one cancels with this one. What is the answer? The variance is n times p minus n times p squared. Sometimes people write this as n times p times 1 minus p. That is the variance of a binomial random variable. Okay, so I gave you the definition, and I said the variance is important. We're not going to do a ton of stuff with variance, but we would like you to know, have heard of it. Why is it important? The variance tells you sort of roughly how spread out things are. How spread out things are. So in particular, something called the standard deviation. The standard deviation, that is the square root of the variance. And the standard deviation controls how far spread out your random variable can be. If you have a small standard deviation, then your random variable is very not random. It's very concentrated around its mean value. If the standard deviation is large, it's very spread out. Let me show you a picture. I have this formula. I took this formula np times 1 minus p and I put it in the computer. Okay? And so what I've done here is I have taken in Desmos, here is the binomial distribution, and I've made it so you can slide the n value and the p value. So you can do an n value like this, a big old n value, and you can change the p value. And I've plotted the mean, which we did a few classes ago. So the mean moves around. Look, it moves around really smoothly. You can have Desmos animate the p value moving. And these blue bars are the binomial probabilities we've been working with for a few classes now. And the mean is right in the middle. And you can see it's kind of like a hump sort of around that mean value. And the variance, it doesn't tell you where the mean is, but it tells you kind of like how spread out things are. And so in this particular case, if I turn these on over here, you'll see there's the mean plus 1 standard deviation and the mean minus 1 standard deviation. And that captures kind of the characteristic width of this hump. Right? So the hump can't be much wider than this thing. And in fact, there's a rule that like I think it's 75% of the probability has to be between the mean minus 1 standard deviation and the mean plus 1 standard deviation. That's Chebyshev's inequality. We're not going to do that. So just know roughly, the standard deviation tells you the sort of width of this thing. Here I can play with the n value as well. Let's make the n value. So you see if I make the n value bigger, it gets a little bit more concentrated. So it's that little hump is narrower. And if you make it less big, then it's wider. Look, there you go. So sort of if you have a large number of coin flips, you can be quite sure that it's close to the mean. Whereas if you have a smaller number, it's more spread out. Okay, that's why we do this stuff. And that kind of gives you a flavor of what you would do in like a higher level statistics class. In the course called Mathematical Statistics, you do all sorts of things like this. This is a good time for any questions or comments about the beautiful picture. Somebody should ask me, for sure you've noticed, this is not just any old shape. This is a beautiful curve. One could make a musical instrument out of this, perhaps a bell. And so I couldn't resist. I did one other thing, which is I put in Desmos this insane formula that involves a pi. Why is pi there? Why is there an e there? But if you put it in, it perfectly matches this. This crazy formula matches this. That's something called the central limit theorem. And again, you'll learn why that works in a higher level probability class. But just to give you a flavor of these things, if you're into this stuff, I think it's the coolest thing ever. This is my favorite theorem of all time. So that's why I had to put it in. Okay. Questions or comments about the picture? We're going to do one other fun activity here in the last 10 minutes. And I have no idea if it's going to work. So, you know, this kind of pen and paper math, I know it works. I was thinking of what other applications are there of these binomial random variables. And what I came up with is something called the mark and recapture procedure. The mark and recapture procedure, as Wikipedia tells us, is a method used in ecology to estimate an animal's population size where it is impractical to count every individual. So this is a method. Imagine you want to count the number of snails in your backyard. In the mark and recapture, you take some of the snails and you mark them, and then you come back later and you recapture them, and you use the marks to figure out how many there are. And it involves this binomial random variable. I give this example because here's a picture of a biologist marking a snail. So he's like writing on the snail. And you have this method of counting them, even if you can't capture all of them, and it is really basic probability using the binomial distribution. And I thought we would try to do this in class. So I have released a number of snails into the room. If you look around, you should see some snails. No, we're doing this a slightly different way. We're going to do this with typos. So instead of snails, you have to imagine that a snail is a misspelled word, okay? So I'm going to show you some text, and you guys are going to count the snails in the text. The snails are misspelled words. So I want you to count the number of snails. And our goal is, like good biologists, we want to know the total number of typos inside my text, okay? So here are the instructions that I want you to do. And I have no idea if this is going to work or not. So I'm very excited. So here it is. Here, I'm gonna pause this so you don't accidentally start putting in. So here are the instructions. Don't read anything else yet. Here are the instructions. So on your own, there's going to be a partner section in a minute. But on your own, you're going to read a paragraph of text, and you're going to write down any misspelled words you see. You must write them down. This is crucial for what's going to happen. So don't just count them in your head. You got to count them and write them down. At the end of the given time, I'll probably give you a minute and a half. You will report how many misspelled words you found. This is very important. I don't want you to say how many misspelled words you think there are. So really just the number that you actually got. So no thinking like, oh, I probably missed some. Really put in the number you actually got. So only the number of words you have written down. That's the thing. I'll give you a minute and a half and I'll show you the paragraph. But are there any questions about how this works? Okay, so here we go. I'm going to set the timer up, and then I will scroll down here. Here is the little paragraph of text. Okay, maybe I zoom out one. Okay, there you go. There's the paragraph of text. You can probably also read it on your phone if you prefer, but you want to look for typos and write them down. So some of the words are spelled wrong. That's what we want you to do. I'll give you a minute and a half. Let's see how you guys do in a minute and a half. So try your best. Okay, put your hand up if you had enough time to sort of read it over once. Maybe not fully, like multiple times, but once. Okay, let me give like 15 more seconds, but I want you to just put in whatever you have, right? So if you spent all day, you'd eventually find them all. I just want the once over. So read it once, get the misspelled words, and put them in. So you can start putting them in now if you're done, and I'll give like 30 more seconds here if you're still going. Okay, there's like 10 seconds left. Put in your thing. Whatever number of misspelled words you found, put it in. If you didn't finish, that's fine. Whatever you got. Okay. Okay, here we go. So I'm gonna, hopefully everybody got their answers in. Did everybody? Okay, let's see what you said. So the number of misspellings I found is, and people said 7, some people said 8, 9, 4 was common, 6. I will tell you, the true answer is higher than these numbers, all right? The true answer is higher than these numbers, of course, because you can only get the actual number if you catch them all, right? So if you are just looking, you will get an underestimate. This is a little bit like if you go into the garden and you count snails, you're not going to catch all the snails, okay? You're going to miss some snails. So these are underestimates. We would like to correct this by doing this capture and recapture method, okay? And I want to show you how this works. If these were snails, I would send you back into the garden to look for more snails a second time. I can't send you to look at the same exact text again, so I'm going to have you guys work in partners, okay? So this is what we're going to do. You're going to find a partner, and then you're going to compare your two lists. And you're going to look at the number of words you both have in common, okay? So find a partner, look at the number of words you have in common, and here is the formula that you're going to use. So you're going to multiply your two numbers and divide by the number you have in common plus 1, and then tell me what that is. What did you get? Well, they're big. Occurring was one of them.
Oh, yeah.
Well, when you do this, you just get the other person. Because presumably they'll have all of them in common with you. So.
That was the number you had was the first one. You didn't see it. And maybe I double counted.
Maybe I gave too much time. Maybe I gave too much time. Okay. Let me motivate you guys to put in your answer. 30 seconds. Put in whatever you got, and you gotta calculate this thing. So you gotta do these plus ones. Plus one, plus one, plus one. Divide them, and then subtract one at the end. So you're gonna need a calculator, and round it down to a whole number. I think there's like 10 or 15 people who still gotta put in something. And we'll see what you guys got.
So each of your estimates should be each independent estimate. You've got two of them, right?
That's right. Yeah. Okay, so. I'm going to reveal what you guys said in a second. I want to explain to you how this works in real life. So, of course, this typo example is made up for the class because I didn't have any snails to release. So in real life, you would go out into the wild, count your snails. Then you would come back like a week later and count the snails. And you would count the number of snails that you caught the previous time because you marked them, right? So you would have the number you found the first time, the number you found the second time, and the number you found both times, which you know because you marked the snails. That's why it's called mark and recapture. And this simple formula will show you where it comes from. It's extremely simple. So if you know all the binomial stuff we've been doing, it's a snap. It's like there's one clever observation you got to do, but it's not a complicated formula. We're going to show you how it works in the first 10 minutes on Friday. But for now, I'm really excited to see if this works or not. So there's some assumptions you got to make about what things are independent or not. And does looking for typos satisfy the assumptions? I don't know. I have no idea. So I have no idea if this is going to work. Let's find out. Reveal submission counts. What did people say? I gotta zoom out or something. Ooh, okay. So 21 or 12 or 9. You'll notice these numbers are all higher than what they were before, right? Before you guys were like 6, 7, 8. These are all a lot higher. The true answer is 10. The true answer is 10. So did we get it right? Did it work? I guess sort of. So 10 was higher than what you said before. Look at this was a little bit closer, I think, than the previous one. 21 is a big overestimate. If you said 21, if you put in a decimal, you did not read the instructions. Okay, 9.8. That's pretty close to 10. So it looks like 9 was the most common thing. That was close to 10. So that's very good. So we'll show you how it works. I think this is such a beautiful thing. Like somehow you can know the total number of typos, even though you guys didn't find all of them, right? You and your partner didn't find all the typos, and yet we kind of get an estimate for how many there are. We'll show you how it works in like 5 minutes on Friday. But if you want to think about it on your own, please go for it. It's not that complicated. Okay, we'll see you guys on Friday then.